In this video, I am going to cover empirical and molecular formulas. Now, the empirical formula is just the lowest whole number ratio of the elements that are in there. The molecular formula tells you exactly how much of each element is in a compound or molecule. And when you're doing a molecular formula, about 90% of the work you have to do for a molecular formula is figuring out the empirical formula. So I'm going to go over empirical formula first, and I'm going to work on this one. 68.4% of chromium and 31.6% oxygen. Now, whenever you're doing this, since these percentages add up to 100, it's nice and easy. You just take those percent signs and you change them to grams. So that 68.4% becomes 68.4 grams. You don't move the decimal point or anything like that. Just change percent to grams, and we're working with chromium. Now what we want to do is get the lowest ratio of moles. So what we have to do is mole conversion. So we start off with putting 1 mole of chromium up top. The molar mass of chromium off the periodic table is 52.0 grams. And when you do this math, it's 68.4 divided by 52.0. And that gives you 1.32 moles of chromium. Now we are going to end up doing the same thing with oxygen. You have 31.6%, which becomes 31.6 grams of oxygen. We want to convert this into moles because we have to compare the moles for these things. Oxygen's molar mass is 16.0 grams. So you do 31.6 divided by 16.0, and that gives you 1.98 moles of oxygen. What I do is match the significant digits. Since these are both 3 significant digits, I want my answers to have 3 significant digits. Now, whenever you write a empirical formula or any kind of formula, you are not going to have something like Cr 1.32 and oxygen 1.98. It's not going to work like that. We want the smallest whole number ratio. And you also don't just round them off. What you have to do is get these to be small whole number ratios. And the best way to do that is take the smaller of these two numbers. So we have 1.32 and 1.98. Divide by the smaller of the two. And what that does is that makes it so you have 1 mole of chromium. When you divide by the smallest of those two numbers, it's automatically going to give you something that's 1, and everything else is going to be bigger than 1. Now in this case, when you do 1.98 divided by 1.32, that gives you 1.5. Now that should seem kind of odd because we also don't want to write Cr, and I'll write a 1 there just for now, and oxygen 1.5. We want these to be small whole numbers. Now, it's easy to take something that ends in a half and make it a whole number. What you do is multiply by 2, and that becomes Cr2O3. And that is the smallest whole number ratio for this. So that is the empirical formula. Now, you may get answers where these two numbers end up being nice whole numbers, and that's nice and easy. You don't have to multiply by 2 then. You would just write down whatever the moles are here and here, you would write that down as the subscripts. You might get some things that end in 1.25 or 1.75 or just 0.25 or 0.75 ending like that. Now that's like saying something is a quarter or 3/4, so you would have to multiply that by 4. But for us, since it ended in 5.5, we multiplied by 2. You also might get things that end in 0.33 or 0.66. That's like saying a third or 2/3, in which case you would multiply by 3. Now for us, for our 5.0 chem class, you're either always going to get whole numbers or something very, very close to a whole number, or you're going to get something that ends in half, like we have here, or a quarter or 3/4, or a third or 2/3. Now what gets to be a little tricky is, say you're doing this and you get something that ends more like 1.4. You're not really close enough to 1.5 to consider it multiplying by 2, and you're not really close enough to something ending in 0.33 to multiply it by 3. You're kind of in this weird middle area. So what I would do is go back and double check all your work and make sure you didn't round off too much. You should either get whole numbers or something very, very close to a whole number, or something very close to that 0.25, 0.33, 0.5, 0.66, or 0.75. They should be close to those things. So if they're not really close to those, double check how you rounded. Now, molecular formula is the same general idea. It is a longer problem, though, in general. Now, for this first one here, the empirical formula of a compound is NO2. Its molecular mass is 92.0 grams per mole. What is its molecular formula? Now, for this problem, this actually ends up being a relatively quick problem because I already gave you the empirical formula in this one. And really, the reason why I did this is to make sure you're paying attention. When you want to figure out the molecular formula of something, what you are going to end up doing is taking the molar mass of the molecular formula, which I'll abbreviate MMMF, and dividing by the molar mass of the empirical formula. Now, this problem is easier because I already gave you the empirical formula. We don't even have to calculate that. I always have to give you the molar mass of the molecular formula. So this 92 is what goes up there. So what we have to do is figure out the molar mass of the empirical formula. Well, we know the empirical formula in this case is NO2. Nitrogen is, there's one of them, it's 14.0 off the periodic table, so that's 14.0. There's two oxygens that are 16.0 apiece, so that's 32.0. You add those up, and it is 46.0 grams per mole. This is the molar mass of the empirical formula. So what we want to do is plug that in to that equation up there. So the molar mass of the molecular formula, which I gave you in the problem, is 92 grams per mole. We figured out the empirical formula, the molar mass of the empirical formula is 46.0 grams per mole. So you do a division here, and it gives you a nice whole number of 2. So what that means is that the molecular formula is 2 times bigger than the empirical formula. So if the empirical formula is NO2, you multiply that by 2 to give you the molecular formula. You get N2O4. And that is the molecular formula. Now, most of the problems are not going to be this short. I just wanted to show you the relationship between the molar mass of the molecular formula and the molar mass of the empirical formula. That is what we are working up to, this equation. So, more like what it will be on the test when you take it is the next problem down. So it has a compound is 40.0% carbon, 6.7% hydrogen, and 53.5% oxygen. It gives you the molar mass of the molecular formula, which I have to give that to you. So that's molar mass molecular formula. It wants to know what is the molecular formula overall. So remember, the main equation we are working with is molar mass of the molecular formula divided by a molar mass of the empirical formula. I gave you this number, but we have to figure out molar mass of the empirical formula. So we're going to start off doing an empirical formula problem. Since these percentages add up to 100% or something very close to 100%, what we could do is just take those percent signs, convert them to grams. So 40.0 grams of carbon. We want to convert this into moles. So we know 1 mole of carbon is 12.0 grams of carbon. So when we do this math, we get 3.33 moles of carbon. 6.7 grams of hydrogen. Remember, just take that percent sign, make it in the grams. Hydrogen's nice and easy. It is 1.0 off the periodic table. So 1 mole of hydrogen is 1.0 grams of hydrogen, which gives you 6.7 moles of hydrogen. For 53.5, change it to grams again of oxygen. Oxygen's molar mass is 16.0. So you do 53.5 divided by 16.0, and that gives you 3.34 moles of oxygen. Now remember, we're working up towards the empirical formula right now, and what we do is divide by the smallest of these 3 numbers. And notice for each of these three, I matched up the significant digits. 40.0 has 3, so 3.33 has 3. 6.7 has 2, so I rounded off to 6.7. 53.5 has 3, so 3.34 has 3 significant digits. You divide by the smallest of these because we want the smallest whole number ratio. That means carbon's nice and easy. It's 1 mole of carbon. And what we get is 2 moles of oxygen. 2 moles of hydrogen. And we get 1 mole of oxygen. So the empirical formula is CH2O. That's the empirical formula. But remember, we want the molecular formula. So what I have to do is I have to figure out the molar mass of the empirical formula. So it's 1 carbon, which is 1 times 12.0. I have 2 hydrogens, which is 1 times 2 of them, because there's 2 of them. 2 times 1.0, which gives you 2.0. And oxygen, there's 1 of them. That's 16.0. So when I add this up, I get 30. That is the molar mass of the empirical formula. So now I want to go back to that equation. So the molar mass of the molecular formula I gave you in the problem, that is 60.0 grams per mole. The molar mass of the empirical formula is 30.0 grams per mole. So that means the ratio is 2. So if my empirical formula is CH2O, my molecular formula is double that. So I get C2H4O2. And that is the molecular formula. By the time you get down to the end here, where you're doing this equation up here, the molar mass of the molecular formula divided by the molar mass of the empirical formula, you should always get a whole number or something very, very close to a whole number. You're never going to get something that's like 1.5 or 1.33 or 1.75 or whatever it is. It's always a whole number. And if you get the number 1 at this point, that's just telling you that the molecular formula is the exact same thing as the empirical formula. So that's how you do empirical and molecular formulas. Most of the work in an empirical or in a molecular formula is figuring out the empirical formula. Then you get the molar mass of the empirical formula, and you do the molar mass of the molecular formula, which I have to give you in the problem, divided by the molar mass of the empirical formula, which is what you just calculated, and see what the ratio is.